Good morning and happy Friday. Welcome to our ICAT Playdate. We're so glad you're here today. My name is Phyllis Newbill. I am one of several associate directors in one of several centers within ICAT. So glad you're here this morning. A couple of housekeeping things before we get started. As always, we are streaming live right now, so what we're saying and doing here is online. And it will exist online afterwards, so I feel like you all should know that. There are pastries and coffee, and I hope you will enjoy those. One of the ways that we justify pastries and coffee is that we get a sign-up list, so when the clipboard goes around, please let us know that you're here. So please sign in on that. If you are a faculty member and PDN or Professional Development Network credit is helpful to you, make sure that you sign up for that and then make eye contact with me, and I will give you your A+ for being here. When you have questions, just wait for me to get to you with a microphone. If you're online, good morning. We're glad you're here too. And if you have questions, please use the questions link. We will get those as quick as we can. Lots of announcements this morning. There's a lot going on. Yeah, I know. Time. Keep going here. I'll try to do them in some kind of order. Today, the College of Art, Architecture, and Design Symposium will be here in this space from 12:30 to 2:30, so if you want to come see what great projects are happening there, hope you'll be there for that. Next week, there will be a show, an immersive experience called Dark Matter in Perform, so check the ICAT website for the details on that. Also, coming soon, The World According to Sound, a discussion on ways of knowing on April 14th at 7, that's in the Cube. There's a beat battle happening in the Cube. This is with Digging in the Crates, which is a great program on campus. That'll be April 21st, 6 to 9. And finally, Vimbuza, which is a project that we've been talking about at some previous play dates, will have an exhibition in the Cube April 28th and 29th, and also on ICAT Day, which brings us to ICAT Day, which is May the 4th. Be with you. Come on over to the Center for the Arts, and we'll be sharing all of our mini seed grants, and lots of existing really cool ICAT projects. Winnie is with us today. Winnie is the dog, and she belongs here. With that, I think that's all the announcements. I'm going to turn it over to David and Braden, and let's see where we're going.
Thank you, Phyllis. Good morning, everyone. Just a quick note, we packed in a lot in this presentation, so we're going to go pretty quickly. So if it seems like we glossed over something, please come talk to Braden and myself afterwards, and we'll be happy to talk to you in more detail. But we're going to try and fly through this a little bit. This morning, we are sitting in a very unique building when it comes to academia. This building was an experiment in many ways, in that it has academic classrooms, it has residence halls, it has a maker space, it has community assembly, it has all these meeting and whatever functionality. Not something that has been tried in academia before, and not something that has been measured, whether it's been successful in academia before. So in this building, you're seeing lidar sensors. You may have seen these walking through this building. We're going to be talking about those today, and we're going to talk about what they captured, and then also how we're going to communicate what that is together. So this is part of an NSF-funded project called Building Ecology. I always forget the examining space, place dynamics in shared indoor environments. I always have to remember that. And hands to all the people in that team. There have been a lot of great products and a lot of great research. It's still ongoing. The LiDAR has been capturing for 3+ years. There have been multiple papers written already, as you can see here. And we'll be doing more work as that too, as more data is analyzed and as we get through this stuff. So our proposal was that as far as the project goes, the big project, shared indoor environments are a unique geographical sort of space where there are shared resources, people move through them, a lot like they do move through the world. So let's measure it. We're using these LiDAR sensors. They were installed in an array around the common areas here, all down the hallway, and in the community assembly space here. This is the original research or experiment area. It was expanded into the little study area over there after the first year, I believe. And this is a real quick representation of what the LiDAR was capturing in real time. You can see people are being tracked, and it's also giving you 3D space. And again, I am flying through this stuff. Here's some of the recorded data, people moving through the space. And the things that we decided to measure were collisions and occupancy. We'll talk more about what those mean a little bit later as far as specifically how we're defining those terms. But here you can see we measured a collision with the LiDAR there. Basically has to do with proximity and pause. And then processing data to measure the collisions in the space to see where people are colliding and where people are moving through. This is 1 hour of paths of people walking through so you can imagine how much data there is. This is 1 hour. But in order to move into studying this data, we needed an accurate representation of the space, and Braden's going to go ahead and talk about that.
Okay, yeah, so when we were looking at the data, we started again with the LiDAR data, and the way that LiDAR works is it like scans everything and makes a point cloud, basically. But point clouds can be really messy, and so that's what this image is here. This is the CID, and as you can see, I think that's the staircase over there. So this mesh is like really sort of messy. It's not dimensionally accurate, and it's not the kind of thing that we can actually design a public artwork within, or visualize the data in a tangible way within. So what we did is we took the blueprints from the CID, from Hanbury, and we actually put these into Rhino, and we laid the floor plans flat, of course, on the XY plane, and then we ended up putting the sections kind of appropriately spaced where they should be, and then actually went through the process of kind of painstakingly recreating the CID in digital space by extruding the model. So again, so this is this kind of glass entranceway over here. And I think this is the community assembly that we're in right now. So we ended up with this kind of 3D model of the CID that has probably a lot more information than we need, but we were trying to kind of like err on the side of caution. And this, again, this is kind of like looking at the blueprints, what this kind of community assembly space looked like. So we then moved on to data visualization. So we have the data, we have a 3D model of the space. How can we visualize that data within the space? And so again, we were looking at two different factors. One of them was collisions. That's when two or more people approach from different directions and pause in close proximity for an extended period of time. So you can think of collisions like being interaction within the space. And then we were also looking at occupancy. So occupancy was just like the time that a human was in the space. So that's mostly the movement of people through the space, but also them hanging out in the space. Okay, so how do we actually go about doing this? Well, there's a few different applications that we can use to kind of make sense of all of this messy point cloud data. Those like long overlapping tracks of people moving, but then also the extremely dense point clouds of where people stopped and talked to each other. So the way that we decided to do this was using QGIS to actually create the initial data visualizations, but then move those sort of like point clouds then into Rhino and Grasshopper so that we could create something physical and tangible from it. And what we ended up doing, so in QGIS, the first step that we did, we were looking at the collision data, which is all these points that you see on the left here. And so that's every single point in this building where someone stopped and talked to each other. I think it was the fall semester of 2023. So that's like one semester of every single point where people have like stopped and talked to each other on the left. I can't remember, I think it was maybe one semester. Yeah. And then so what we did is on the right then, we ended up making a kernel density analysis, so basically like a heat map of all of those points. So basically, points have a certain radius where they interact with other points, and if they're dense enough, they kind of create this darker tone. So you can kind of see the areas where people were heavily colliding with each other are the areas where the heat map is darker. And then we converted that into a grayscale image. And we used a function within Grasshopper. Grasshopper is the kind of visual coding language for Rhino. Rhino is a computer-aided design software. So we used this we set up this script within Grasshopper where we were basically taking the pixel value of each of the grayscale image, each of the pixels in the grayscale image. And the darker that a pixel was, it correlated with a higher z height for a corresponding point. So basically what we ended up doing was creating this kind of like 3D topological map that was a visualization of that data. And so you could see on the right over here, you can kind of see the corresponding sort of peaks that correspond with the darker parts of the heat map. And so on a larger scale, this is what the entire sort of data set looks like of the entire first sort of common area floor of the CID. Again, it looks very much like a landscape. And so we also did a very similar thing with the movement data. So we took all of these tracks that you see over here on the left, and we used a line density analysis tool within QGIS to, again, create a grayscale image that we could better visualize this data. And we ran it through the exact same process, and we ended up, again, with kind of a very, again, not quite as much of a topological map as the collisions, but a really interesting three-dimensional representation of how people move within this space. So you can kind of start to see where people like stream and flow through the space and how they go around corners and weave in between the furniture. And you can see, I think those like pockets on kind of the upper middle right, those are the columns of the space that people kind of move around, as they're avoiding them. And then sort of a lot of the like smaller pockets that you see are actually the furniture, the tables and chairs and stuff. So that was then visualizing the data, but then we also needed to take these kind of like messy, sort of like landscape looking like meshes, and again, run them through Grasshopper to kind of smooth them and refine them. So what we did is we did form finding within Grasshopper, we did dynamic mesh relaxation, loop subdivision, mesh smoothing, and circle packing. I'm gonna kind of gloss over this for the sake of time. It's kind of complicated, but basically what you end up doing is you end up, this is circle packing. This is like a little GIF of how circle packing works. So meshes, when they're first triangulated, are very messy. The mesh triangles are kind of placed arbitrarily to approximate the surface. But when you perform a circle packing, what ends up happening is those triangles a circle is kind of made at the center of each of those triangles, and the circles are adjacent to the other circles of the other areas of the mesh triangles, and they kind of like wiggle in space and try to kind of find a more even spacing or a more even packing. And that's all performed in Grasshopper. So you start off with a mesh that's like this, pretty messy, and you end up with a mesh that's more like this. So it's more regular, more aesthetically pleasing, and easier to fabricate too. So again, start with the mesh on the left, and we want to move towards a mesh that's like the one on the right. And the benefits of having a more regular mesh, again, you can start to then actually build more visually compelling artworks or structures off of that sort of mesh. Okay, so that's all kind of abstract, but how does that actually translate to how we were treating the mesh in the space? This is a very thin slice of the CID that includes the stairway over there, and the red kind of form or surface that you see is the mesh that's approximating the collisions within the space. So what we ended up doing is we took that mesh that approximates the collisions, we located it exactly where it was within the CID. We then defined a boundary with which we could actually trim that mesh. So we trimmed the mesh, got rid of the boundary. We performed the same operation with the movement data. So the movement data was just higher up, so we could kind of visually make them distinct from one another. And then what we did, this might be kind of hard to see, but we found the area of all the mesh triangles that's kind of represented by the little points. And we projected them onto the mesh that was directly below it. So again, we're just taking each point and pulling it down until it hits the surface of the second mesh. We're then drawing a line between those 2 points, and we're finding the distance that each of those lines, or the length of each of those lines. So as you can see here, you have lengths like in inches. There's like 40 inches over here, but 36 inches over here. And this is kind of a view from the side, so you can again see how the 2 meshes are different and the different lengths between them. So basically what we did then is we measured all those distances and used them almost as like an attractor within Grasshopper. So the smaller the distance, the larger, or no, the smaller the distance, the smaller the aperture size. So for each of these lines, basically like the closer these 2 meshes were to each other, the closer the height of the movement data was to the height of the collisions data. The closer that distance was, kind of the smaller the aperture size of one of these sort of cells. This will kind of make sense in a second. Okay, so the sculpture's form kind of is taking the form of the movement data, while the aperture size of the cell, the opening of each of the cells, is more determined by the distance that's between each of those 2 meshes. So it's a little bit zoomed out here. It's a little hard to tell, but hopefully you can kind of tell on the far left side, the aperture size is smaller. And then in the middle, the aperture size is larger. And then it goes sort of back to a smaller aperture size on the far right. So again, showing that shift kind of in the data. And this is a little bit of a closer up look. So again, distances that were like higher, so 49 as the distance between the 2 meshes, correlated with a larger aperture size, and a smaller distance between the 2 meshes, like 33, corresponds with a smaller aperture size. And this is all kind of automated within Grasshopper. So we were trying to kind of visualize both of those 2 data sets within one sculpture. So the height of the sculpture, again, is where people move through the space. And looking at it from the side here, you can really kind of see, of course, the higher up the sculpture is, that's where more people were moving through the space, which makes sense because it's kind of located in this little hallway over here. And less people were moving through, of course, closer to the columns or the pillars over here, and less people were also moving through the closer you get to that glass wall, kind of demonstrated by these students walking past. And then of course we needed to also start thinking about like attachment. How are we going to attach these things within the space? So we ended up creating a couple renders, kind of like on-site renders of what this sort of artwork might look like within the space. And one thing that we were really trying to work with was how could we make the sculpture kind of like tuck in and out of doorways to kind of better approximate how people actually move or travel within the space. Here it is from another angle. Here we are like looking at it from directly ahead. This is that north vestibule over there, so you can kind of see the variation in Z height of the sculpture as it's suspended. Here's like a few more renders from within the space. Okay, so I'm going to hand it back to David to talk a little bit about the...
So as you can imagine, something like this, you're probably like, oh, you're going to hang a bunch of stuff above people in a hallway in a public building. How's that going to work? We have the same question. We've been considering this from the very beginning. So as far as the design and placement of any physical infrastructure and also hanging hardware for suspending this thing. So what you're looking at here is sort of a map of where health and safety things are, the sprinkler heads from the plans versus the as-built sprinkler heads, which somehow are different. Any architects in the audience will know that that is a thing for some reason. Excuse me. We need to consider exit signage, visibility for egress. We need to consider camera sight lines because there are security cameras in this building since it is a public building that's accessible after hours. So those are all considerations that have to be considered. We've definitely been considering fire safety. Things have to be 18 inches away from sprinkler heads. Nothing's flammable or absorbent, so it's not going to gain weight once it gets wet. And it is more than 50% open, so it should allow water to get down to where it needs to go if in case of a fire. The way that we're thinking about suspending this thing is using a substructure from the structure of the building. On the east side of the hall over there, there already is a substructure that will be able to hang. You can see the black pipes that are hanging there. We're proposing adding another substructure on this side that's hanging from the building's beams in order to hang this structure, which honestly isn't that much weight. It looks like a lot, it looks big, but when it's spread out over such a large area and the material itself is very light, it's really not that much load at all. We're estimating with planning to use 0.04-inch thick aluminum sheet metal that this thing's going to weigh around 1,200 pounds across the 180 so feet of its length, meaning that like it's only less than 1.5 pounds per square foot, which depending on how many hanging points we end up using is only a few pounds per hanging point. So we're definitely going to be picking hardware that's rated for that, but I mean, you could almost hang 4 pounds from a paper clip. That's, so we're making sure that everything is really thought through here as far as overhead safety and fire safety.
Okay, yeah, I'll be pretty quick. Okay, so again, all of these overlapping concerns were kind of going into how we were actually designing this thing, knowing that we needed to keep it lightweight, knowing it needed to be suspended, knowing it needed suspension points to hang from. So when we started with fabrication, we started working at half scale with a paper model, and that's on the floor down here. And this was kind of to test whether, like, visually, you could kind of see the difference between the aperture sizes closing and opening. And we decided, of course, to move through. The paper model was laser cut, so super handy to have those laser cutters there so we can kind of very quickly iterate through things. But when it came time to actually make the this kind of full-scale section of the model, we needed to use the CNC plasma cutter within the CID makerspace. And so what we ended up doing was taking all of these smaller kind of components that you can see here on the right, nesting them very efficiently because we don't want to waste a whole lot of sheet material. And then we ended up cutting them out and assembling them. So each of these is kind of modular. Each of these sections the whole sculpture is made out of flat sheet metal, and it's all sort of modular, so it all bolts together. And each piece is also totally unique. So thanks for catching that. So because again, so none of the triangles are the same size, none of the triangles meet at the same angle, and they're all different heights. So the entire sculpture is going to be like 2,500 unique parts. So each part is going to be labeled, and then will need to be then assembled. And each unique part needs to land up in its special, unique place. So lots of challenges with this, of course. We're going to end up kind of shipping this out to someone else to laser cut it. We're going to use probably like SendCutSend or some sort of service like that that has industrial sort of CNC fiber lasers. Do you want to talk a little bit about? Okay.
So our big kind of next step right now is to go up through administrative approvals at the university to make sure that we can actually go forward with this thing now that we have some semblance of what this thing could actually be. Before it was a lot of swirling ideas, and nobody wants to hear swirling ideas. They want to know, what are you going to hang over people's heads and how are you going to do it? So we're working through that right now, and then we'll refine the design based on that input, and then do all the other things that you would need to do in order to build something. We're just going to gloss over this because we're out of time, but feel free to come up to look at this and talk to us a little bit more about it. Thank you very much.
Y'all did a great job leaving time for questions. Thank you. What questions do we have?
Okay, thank you. So how were you able to know by the tracking system if people were having unplanned encounters? That's one.
Unplanned?
Unplanned.
Okay, there's no distinction between unplanned and planned encounter. It's really only measuring whether people came from different directions and stopped for a certain amount of time. There's a threshold there. So there's no way to know because it's anonymized. We don't know people's intention or anything. It's really just measuring purely movement.
Yes. Thank you. Okay, so you claim that you can encourage these interactions to foster collaboration and relationship development in the paper.
Which paper?
The lidar-based detection of analysis of serendipitous conditions.
Oh, okay. That was not my paper. That was the Tom Pingle's paper. Not this Tom. Tom Pingle was another geographer that was on the project that helped design the lidar system. So unfortunately, he's not here to talk about that. But yeah.
Yeah, but the idea is that this architectural work kind of, like, it's oriented to improve the relationship between.
That's the idea, and so the larger study was trying to measure that, if it was a thing. So there's also a human-based social study happening where there's interviews and surveys being conducted of residents and users of the building. So that's also being researched as well, like sort of in parallel with the physical movement of the space.
Hi, thank you. This was a really, really cool project. And I became curious as I was watching you all, wondering if, is there a way to measure, or maybe it's irrelevant to think about whether this structure impacts the temperature, or perceived temperature, or even the space, how we perceive a space. Like here I have this really high ceiling, I perceive in a certain way. Does that will then change how people inhabit and interact in the space? Yeah, thank you.
Yeah, that's a really interesting question, and that's one that we've kind of been talking about too. It would be really interesting to kind of build it and then continue running the lidar data to see if it affects how people move through the space, how they interact with the space, but then also try to figure out what sort of effect does it have, like on the temperature of the space, because again, this much aluminum next to the ceiling will kind of probably act like a heat sink of sorts, and it's also going to redirect light. So it's going to reflect light in really interesting ways, and it will probably also affect the acoustics of the space too, like I was talking with Brandon about earlier. So it will probably have some sort of quantitative and qualitative impact on people's experience of the space. Yeah, we're not sure what, though. Hopefully people like it. I can kind of keep going off of, unless Tom, you know.
So really great talk about the process sort of making the sculpture. Can you talk a little bit about the process? And this might be a question as much for Tim. You know, one of the things we look at when we're evaluating seed grants is, you know, we don't want things where it's like, oh, there's the science piece, and then we wrap the art around it as an after effect kind of thing. And can you talk a little bit about the early data collection and sort of the visualization before you use that to drive the art, and how maybe that impacted the way the scientific research side of it was looking at things?
I mean, I'm happy to give a couple of...
Wait. Hi, Winnie.
I'm Tim. I kind of lead the data collection part of this project, but my collaborator really leads the LiDAR portion of this project. I have been so impressed with David's patience with this. He's kind of like watched this project for a number of years, like collect data. He's attended meetings and he's seen what we're doing. And then at some point, we just like pushed all this data and to him, and like David and Braden, they have done this entirely by themselves. I'm so blown away by it. I'm not sure that this is a textbook example of like science and art like really woven together incredibly mindfully at the start, but I'm like so blown away at this moment to see what they've done. I'm very proud of it, yeah.
I think too that for me, it's really interesting to be able to design and hopefully install something in the place where the data was collected, right? So here is a physical manifestation of years of data that was collected in this space, and you're standing under it and walking through it every day. That's not really an opportunity that gets to happen. Like, here is the manifestation of the science of this building right here. So I think that was really what's, and because I was part of the project from the beginning, like I helped design the layout for the LiDAR sensors, helped install them, you know, helped test the LiDAR sensors and how we were going to process the data, and really, you know, that whole system, that, you know, it's not just a glom on at the end sort of art product, which can happen in these sorts of collaborations.
Go ahead, and then
Oh, yeah, I was just going to say too, like, I feel like looking at this as like a longer term thing is interesting too, because of course, like, architecture in the built environment happens. This is a super useful and important post-occupancy study that then happens within the space that reveals better how people interact with architecture and use and move through architecture. But I think it can then also then feed back into then how we're designing the next sort of building like this, and knowing that humans actually move more like that than they do like that. Like, what if we designed our buildings to look more like that? I think that's like the most interesting part to me, is then how it can kind of feed back into itself.
with, you know, that assuming we get all the approvals that we need and they're able to install this summer, I will spend so much time next year talking about this installation with students, with administrators. We'll do more presentations about this. So I think a lot of the fusion of science and art and storytelling will occur after this goes up. And I think people are going to be really excited about it. Yeah, including architects.
We are at time, a little past, that's good. Thank you for the good conversation, and I know that there are still some snacks and coffee available, so please continue conversations. We'll be back next week for more mind-blowing ICAT things and more pastries and coffee, so we'll see you then. Have a great weekend. Thanks so much for being here.